All right, so now we're getting into matter and energy. So we're looking at energy now. You're going to complete Travelogue 2.2. Remember, just do the before, don't do the after. We'll do the after we're done with all of matter and energy. Okay, so energy. What is energy? Well, it's the ability to do work, any work. So there are different forms of energy. So we have kinetic. That's the motion. Like if I go like this and I drop my calculator, that's kinetic energy. It's moving. It's actually like there's movement to it. I'm kinetic energy right now. I'm expending because I'm moving. Potential though is, say I have this right here. It has the potential to move so far. So there's so much energy stored up here so that when I release it like this, that was kinetic. So it goes from potential to kinetic. Potential is stored, gravitational, could be chemical, can be electrical, whereas kinetic is motion and mechanical. And then you got radiant energy. That's from the sun. That's how we get some heat and light. And how this is usually measured, the units, you will see calorie. That's the non-standard way of saying energy. You see calories like in living environment. You see calories on the back of labels. But in chemistry, we use joules. That is our standard indication of what we are going to use, right? So who came up with this? Well, Lavoisier. Sorry, let me move this down. Lavoisier, he's the one who came up with the different laws. And one of the laws is that energy can be transferred and transformed, but it can never be created or destroyed. So energy is always there. It's just transferred or transformed into something else. You can't create it. You can't destroy it. You can't get rid of it. So the big thing with this is temperature. Temperature and heat are two totally different things. Temperature is the average kinetic energy of a particle in motion. So it's the average kinetic energy in a liquid. Average kinetic energy of your body. That is a temperature. Independent of sample size. So this is an intensive property. It doesn't matter what's going on. It is independent. It's solely based on itself, based on the sample size. Or sorry, not based on the sample size. So in my room, I could have water bottles all throughout all different sizes. You could take the temperature, the kinetic energy of all of them, and they will be the same because I'm in the same area. It's independent, intensive, and it's measured in degrees. Heat, on the other hand, totally separate from temperature. Heat is the total energy in the system. That's the energy, the joules of the system. And it's dependent on the size of the system. So this is extensive outside. It depends on how big it is. And it's measured in joules. So like I said, the total energy, that's the joules we're looking at. Temperature, that we're not measuring in joules, we're measuring in, hopefully, Kelvin, K. Why do I bring this up? Well, temperature is taken in either Fahrenheit, which we typically look at. Celsius is the typical for sciences, but we actually go based on Kelvin. So Celsius is the relative scale based on freezing and boiling points of water. That's 0 is freezing, 100 is boiling. Kelvin, on the other hand, that is the absolute scale, where absolute zero is there's no motion. So there's nothing going on. And I believe, so far that I know, we have yet to be able to hit absolute zero on Earth. You cannot stop everything from moving on Earth. In space, yes, you can. But here, nope. Molecular motion ceases to exist. Like nothing. There's no movement whatsoever. And like I said, cannot be reached. Now, here's the thing. Because we measure most things, you notice we don't have a Kelvin scale on our thermometers that we did earlier. We used it in the other lab. we have to convert to Kelvin. And how to do this, in your reference table at the bottom of page 12, where it says temperature, you have Kelvin right here. And it gives you the nice little formula. So it does say degrees Celsius right there. It's got Kelvin, and it gives you the formula right here. Very important. So right here, we are looking at the different thermometer readings on this page. Kelvin and Celsius temperatures have different readings, and they differ by 273.15. We are not going to do the 0.15 in chemistry. We're just going to cut it off. We're going to round it up to the nearest ones position and have 273. So to do this, you can get the difference between a Kelvin and a Celsius by converting. Yes, we're converting. We're doing math, but not too bad. So for Kelvin, we are going to do Celsius plus 273. For Celsius, though, you have to do Kelvin minus 273. It's just reorganizing the formula. For Fahrenheit, yeah, we're not even going to try Fahrenheit, so we don't have to memorize this. This is why it's not on there. We don't do Fahrenheit. We go by Celsius. All right, so if you were to do that, it'd be 180 Fahrenheit over 100 Celsius times the degrees Celsius plus 32 degrees Fahrenheit. We're not doing that, so don't worry. All right, let's do a little bit of conversion. What is 163 degrees Celsius on the Kelvin scale? We're going to use that formula. So the first thing you're going to do is you're going to plug in into the formula right here. Plug in the information you know. We have 163. We're going to plug it in where the Celsius goes. So all I have to do now is add it up. And I think this is a simple addition. It'd be 6 is 12 for 426 degrees Kelvin. How about negative 62? So again, you know negative 62, you're going to plug it in the formula. So when I do that, it's simple calculation. Should get 211 Kelvin, right? Because it's 273 minus 62, right? Room temperature is approximately 298 degrees. I'm going to plug this in. So it's 298 degrees Kelvin. What is it in Celsius? So we got to do the reverse. So I'm going to take this and show how you can plug in the reverse. All I got to do is I got to get this by myself. So it's degree K minus 273 equals degrees Celsius. Sorry, that was really, really horrible. I'm going to fix that. Degrees Celsius. We have 298 minus 273 will give you the degree C. Let's see. That's 5, 79, 2, 25 degrees Celsius. Right like that. If the temperature increases 30 degrees Celsius, what is its Kelvin increase? So if you increase 30 degrees Celsius, you're going to increase 30 degrees Kelvin. The relation keeps going up. It doesn't matter how much or what number it is. If I increase, I can show you right now real quick why it doesn't matter what number it is. So remember, Kelvin equals degrees Celsius plus 273. I'm going to start with 0, right? So if I do 0, Kelvin equals 0 plus 273. Kelvin will be 273. If I increase my Celsius by 30, it'd be Kelvin equals 30 degrees Celsius plus 273. And that would be 303. So let's see what happens here. If I add 30 to 273, I get 303, right? So it doesn't matter. It's the same. All right, so we are done for right now. Give me 1 second. When you're done with this, you're going to be doing the green page. Flip to the green page, right where it says matter and property. Please complete 1 and 2. You don't have to do 3, 4, 5, 6, and 7 yet. I would definitely like you to please just do 1 and 2. All right. That is it. If you have any questions, please don't hesitate to email me and ask me questions. And I hope you have a great day.